come much later. Let's take a look here. Here's our raw temperature data. Here's delta T normalized input power, so here's our energy gain, this to this. And as we go to higher input powers, notice the energy gain falls. And we saw that from the optimal operating curves. As you go to higher power, you're getting electrolysis. If it's water, and if it's here, we're creating other pathways that are not what we want. Yeah.
What happens if you keep your input power constant for a longer period of time?
Pardon?
What happens if you keep your input power constant
It'll
for a
stay
long
there. Unless, we recently have found out that if that electric polarization occurs, if there's a delay, then it keeps going up. That's something we just found out. So we haven't explored those, but usually what happens is, I'll show you some that are a long time. The reason we do this as an exploratory mode is we want to find out where the optimal operating point is, and then we'll drive that for a longer time. Here's another one where here we do on the control of two power levels. Here we do the nanor, and here's our ratio. And you see this comes back to there. Here's another one. Again, this ratio to here, this is input power. So here's our calorimetry. When you have full bore calorimetry, your energy gain is this. Okay? So if it's a delta T or heat flow, you take the ratio of the device to the control. If it's calorimetry, you take the device to itself. And here's our energy gain. Here's another one. And this is where we have strong polarization effects. See, when we do the calibration pulse to the ohmic control, the current immediately follows the voltage. But for some reason, our best nanors, I don't know why, but the current comes later. We are seeing possibly ferroelectric and ferromagnetic effects in these materials. And there's a whole material domain that just has to be explored. And that's in fact what started coming out at ICCF 18 from a number of people, like Dr. Kim, myself, and others.
It seems to be that your power gain ratio is better at low power inputs than
Yeah. Not always the lowest, but the lowest that we showed here, yes. That's why it's very critical that you understand your system to know where to drive it. Okay, what we're looking at here is heat flow. So this is like, okay, so here we're looking at heat flow. So we got ohmic control, nanor, ohmic control, nanor, ohmic control, nanor. So we're seeing different energy gains here by the heat flow. As I said, we're seeing very unusual effects if there's a delay. So normally, to answer your question, you see this would be flat. But in the one case, or the two cases where we've seen a delay of response, it seems to keep going up. And I wasn't smart enough to keep it running then, but we'll go back and repeat it. I could just keep going through these. Let's just go to Series 6. In fact, let's jump ahead. There's just so many of these. I apologize. Let's go to the one that we did at MIT. So here we are at the demo. This is 6.3. These codes are just how we treat them. There's a lot of post-processing, and that's what the second code is. So what we did is we set it up in Peter's lab after the course. And what we saw that day was by delta T, we had an energy gain of 12. It's not 12%, 12 times. By calorimetry, the same heat flow detectors were working that day. And by calorimetry, a gain of 14. Here's what we saw. Here's the delta T. Now, it's not delta T normalized input power, so that's not going to be a straight line. It's going to be a rise. So here's our input to the control. Here's our output. Here's our input to the nanor. Here's our output. And if you want to see what the gain is, you've got to normalize it to input power so it becomes a straight line. And now we can take this ratio. Now see here, the lowest level is not the highest. It just depends where it turns out. So when we went to, if we were going to exploit this for an engine or for electricity production, then we would drive it here. And here's the calorimetry for that run. See, there's a nice match here. And here they start separating. So this is our excess energy. This is our input energy. And the slight increase here is heat output, just above that. Later that night, the evening after the demo, the heat flow turned on, and that also showed excess energy. So that evening after the course, I mean, I could keep showing you, I'll show you a few. We ran for 5 months. And So here, for example, delta T normalized, here's our energy gain, is this to this, this to this. It's fairly reproducible. And it's a bit more reproducible than the flyers I handed out. Here's our heat flow. Again, we can take the ratio of one to the other to get the energy gain. And here's the full bore calorimetry of that evening. Here's our energy gain. It's this to this, this to this. You don't take the ratio of that to that. It's calorimetry. Anyway, I'll just go through some more.
Are you shutting it down periodically?
Yes, this was not run continuously. What we did is a series of, first we did a series like this. But a lot of people ask, why did we use low power? Why did we do it for a 2-hour run around? The answer was of course. I wanted it to be run safely here, overnight. We didn't know we'd go for 5 months at the time, but last time we did go for 5 days. And during one of the days, the Tuesday, someone disconnected the power supply, connected it to a chair. I mean, I just wanted it to be as safe as I could. I figured if it was under 2 watts, we'd be all right. And so that's why we did it. And the reason we did it for 2 hours was so that we could get one complete run for a course, an ohmic control and the coefficient. And then Peter suggested do a slightly different thing, which is what we did is we do an ohmic pulse, wait, do a pulse to the nanor, wait, and 2 more pulses, and there's the calibration pulse. It doesn't matter how we do it, we still get the excess heat out, okay? In one way, we have a little higher duty cycle. Here again, this is looking at the delta T normalized input power, so this ratio is our energy gain. And I think we got the heat flow as well here, so we got, again, that's our energy gain. And we even show excess heat by the calorimetry. And we take this ratio for our energy gain. Okay?
Did you measure chemical composition when you started and when you finished?
We should, but we haven't. And another thing we haven't done is for every nanor, it would be nice if we had the ability, time, and money where we did a run of virgin nanor plus D plus H. I mean, that's what we really want to do, but there's just a minimal amount of, go ahead.
I'm sorry, on a few of your slides, it looked like when you had multiple runs, the excess power was decreasing monotonically across
You're
the
very
multiple
smart,
runs.
very accurate, and we'll talk about that.
Okay.
You're way ahead of me. And what's most interesting is when we added a magnetic field, that pattern disappeared. That was the big thing at ICC F18 we're coming to. All right, so here's in May. We're not getting as much out as we did in January, but we're still getting excess energy out. Here is the, let's see, May 27th, and we're just looking at input power and delta T. So for the same amount of input power, more or less, we're getting a much higher delta T out. If we normalize the input power, it's almost a straight line. We can take this ratio to get the energy gain. And here you do see the drop off from the bottom. Here's our heat flow, again normalize the input power. And here's our calorimetry. So we take this ratio to this to get the energy gain. And here, again, notice that these curves separate to indicate energy gain. And it was running, this is February 14th, a year later. We're still getting excess power out, not as much. Okay, so we looked at the impact of a magnetic field on it. I showed you that cartoon where we put the materials in a box so we could put different magnets on, and this is what we saw. This is our incremental gain. So here's our energy gain. We get energy gain to begin with. Now remember, we started off at 14 to 20. So it's gone to June, it's decreased to 8. Okay? We've been running for 5 months. Tiny magnet doesn't do very much, but as we do larger magnets, and the largest magnet in Peter's lab, we're going back up. Now, I decided I would try something interesting, which was using very high magnetic fields that we flip. And so we took 2 Tesla fields, flipped them every 1/10 of a millisecond, flipped it once per second, and did that 4,000 times. And this is what we get. This is the paper we presented.
You mean changing the polarity?
Yes. Well, changing the direction of the current.
Yeah.
First turning it on, turning it off, and then going back.
Don't you get a huge battery one?
the direction of the magnetic field was the same each time. It actually goes on, off, on, off, on, off. And the time constant is 10 milliseconds up and 1 second waiting in between.
Don't you get a big power to low voltage?
Oh, we do. We do. It generates about 40,000 volts at 5 centimeters to flip 2 Tesla at a 10th millisecond. And most of our data for current,
You need a
I don't think I want to talk about it. I think I'm just going to skip it.
big snowy.
It has to do with the secunding of the machine. We'll deal with that another time. Here's what we saw. Here is our calibration pulse. Here's our ohmic control. Here is the input to the nano, another calibration pulse. So we don't do very much to the ohmic control, but and remember that's right. They're both the same distance from the magnetic field. They're tied together. So we're putting the same current in both, but we're not. Sorry about that. But we're not seeing it on the ohmic control like we are in the nano. Except for the difference in materials, same current, probably induce same voltage. Actually, it's probably slightly different current because the impedances are different. The induced voltage is probably the same. Anyway, here what we see is there were two effects. One is we see a massive synchronous increase of output power. This was very exciting. And it was matched by the excitement that we found we permanently changed the material. So for example, here was no additional field, which was higher than before, as I'll show you in a bit. Here's with the magnetic field, and we're doing something later. We went to higher fields. Here's our ohmic control. Here's the nano ohmic control, nano bing. This is we're flipping 0.4 Tesla every 10th millisecond. And we saw it both for delta T normalized the input power, heat flow normalized the input power. And here is the interesting thing that you brought up. Here we see no magnetic field. Here we put on the magnetic field. There's no magnetic field here. And look, in the past, it would have come down like this. That's not what we see. We see a cycle. For some reason, once we magnetize these devices and then treat them, they are interacting with themselves. I don't know if it's a reorganization of material, a restructuring, a redistribution of the fuel inside, but never have we seen anything like this before, where we have always seen where there's a slow fall off and exponential fall, and here we're seeing something else, and it continues. So for example, here there's no treatment either. There's no more magnetic field here, and yet this isn't doing what it was doing before. Before it was well behaved, it was falling off nice and slow over months. That's not what this is. We've entered a whole new realm. Just as going to nanomaterials gave us a new realm, adding magnetic fields does too.
Now, is this with nickel or with palladium?
This one, I'm going to show you some of each,
Okay.
but this one is palladium with deuterium.
Okay.
The biggest effect that really surprised me was the impact on the optimal operating point curves. In the past, we've looked at these optimal operating point curves for, it turns out they exist for making tritium, they exist for making helium-4. It turns out they exist for making heat. And what we see is, as I've shown you, you don't really want to go beyond, because in aqueous systems, we activate electrolysis, which we don't want. Here we have limited loading. In nanomaterials, we may be activating other pathways we don't want, but they all tend to fall off. So I thought, this is out of my lab notebook, I thought when I put on the magnetic field, this would rise. Boy, was I wrong. We got two of them. Instead of one optimal operating point, having submitted a nanor to a large DHDT field, we get two optimal peaks. We get a new one while the field is on. Never saw that before. And then, here's classical fusion. Here's our normal. Here's what we used to think was the cat's meow. It turns out that when we put on the field, we first get this, and then when we turn the field off, we get this. We are improving the amplification of energy gain of these materials by treating them. So we call this a different class of material. We call these M-nanors, for magnetically treated nanors. Let me show you this a little more, so to make that clear. These are new, here's our old OOP. Now, this is sort of proportional to input power, but not exact. These are actually the numbers that we're giving to drive the thing. But here's what we used to like, and here's our new enhanced output. So we see a synchronous effect, and we see a tardide effect. Tardide means we do something and it comes out late. It doesn't come out synchronously. It comes out metachronously. So here, this is our synchronous rise, but after time, it disappears. We don't see it. Instead, this falls down and we get this.
There's never a Faraday low voltage going on while you're doing heat measurement. DHCT non-zero wattage.
During the red one, here it is. When see where it says new? During the magnetic field application, we get the blue. After the application, we get the brown. So here, I mean the red. I apologize. This is during the treatment. This is after. This is the metachronous effect. So this one is actually seen during the treatment, and later it would have done that.
Mitchell, how long does that effect last after you've treated it and run it, you find that it loops?
We find it at least weeks. I've not looked long term.
So there's clearly not a storage in terms of polarization of particles. There's no way you can store that much energy in there.
You could store polarization of the magnetic material.
But for that long?
Magnets,
Oh, okay.
I don't think that's a problem. I mean, it could be we're creating a series of domains in this thing where the domain size changes as we treat it, or there's a redistribution.
Well, I'm
not
wondering
sure
if
what
you're
it
converting
is.
a paramagnetic material in the case of loaded palladium into a ferromagnetic material.
Yeah, have you run a VH characteristic on this with a
I haven't.
with a magnetometer?
Not yet.
Okay.
I made this up. I think cold fusion is mediated by phonons, and my fantasy was maybe we have a second oil that allows, I guess the way I look at it is these deuterons interact with high loading and activation, and there's some kind of activated stage that occurs. Until it goes down to the ground state, it's filled. So as long as we can get things down to the ground state, we can keep going up. And so I thought what was happening was maybe we were making magnons or something. Who knows? Anyway, we saw an energy gain of 22, a 4 times increase over what we were seeing immediately. And so generally, to add magnetic fields will increase your energy gain. All right, let's show you a little more. What I tried to do was I took one of these nanors. We have all of these incredible people working with CR39. And I leaned on Larry and Pam to give me some CR39s. And what you see here is the nanor and an ohmic control without the thermal material around it. The thermal material would come into about here up to about here. But I wanted to strip it off so you'd see where the CR39 is. So we put one right over the nanor, we put one inside the chamber, and we put a third one in my lab notebook. And let me show you what they showed. Here's where we put it over, and we can see this in output. Oh yeah. And what we saw was above the nanor, if we look at the counts, this is what we saw above the nanor, this to the nanor. This was that, the second one here. As far away as here. And this was in my lab notebook. So we've shown output from that. Well, can we image it? Well, I tried and we did. We looked at the pitting, at the freak things, and what we found was if we took the large pits, we could actually image the device. And here's where we put the CR39. And that's where we saw the image on the chip. I tried to do some measurements of gammas. I'm too embarrassed to talk about it, so I'm going to skip. Basically, I should show you one thing. There does appear to be, maybe I should tell you. Here's the background. I'm new to this. I mean, even though I'm a radiation oncologist, you get into a new field. And so I'm a little uncomfortable reporting it, but maybe I will because you're smarter than me and you'll take it farther. The problem with these materials is they put out less radiation than you do. In this room, every one of you is putting out about 80 nanosieverts an hour. You're probably getting the biggest dose you got all day by being here at this meeting. So the problem we have is, at full bore, we measured that the nanors are only putting out 8 nanosieverts per hour. The only reason I even got to measure anything was we set up an Arduino system to run them so we didn't have to go near them for 3 months, and that's how we get the data. So this was the background with no humans around, and what I did is I put a high-pass filter on here, so we would see very little input, except for the fact, I put it so high we went to 0, except when we activate the control, and we saw it only during the nanor. We saw, here we only saw it while the nanor was treated here. And when we look at the output from that, again, it's a real primitive way to do it. What we see is the incremental counts beyond our high-pass filter, okay, is this as we put more and more power into the nanor. And we also saw some, during the avalanche, we saw output, and this is our background. Anyway, the important thing is you emit more together here than the nanors do. And the nanors are only putting out 8 nanosieverts an hour. Okay, so now we can finally get to what we're talking about. I want to show you the breakdown on both sides. I apologize for taking so long. Again, what we're going to look at is calibration pulses. We're going to look, here's an input. This is nanor 7.1. And APO means we haven't hyperloaded it yet. What we do is put the nanomaterial in. It's not hyperloaded, call it APO nanor, not quite together yet. So here's our input, here's our output of the old control. Here's our input of the nanor, output of, it's already doing pretty good actually. Let me jump ahead. This is, let's see, nanor 74. This is a palladium material. So here's our input to the OMA control. Here's our input to the nanor. This will be our ratio if this is input power normalized. So here's our ratio of energy gain for a very tiny amount of input power, but it's pretty large, yes.
Eventually, you're the only person I know who has a view graph with energy gain more than 100 on it and skips past it in a rush.
There's a lot of There's more. There's more. I mean, it's reproduced. Look, here we do one after what?
Just to add to his question, are all the ones 100 which are stagnant, are all those with the fields being changed?
No. None of these are in nanors. Excuse me, no magnetic fields in this. These have never seen magnetic fields. What I began doing after ICCF 18, was to go back. I mean, who knows if we picked the right nanomaterial? So I'm actually looking at different nanomaterials and different ways of hyperloading before we get picked into one thing. So for example, let's just look at some more.
You were up past 100.
Pardon?
And you were up past 100. Again?
Whatever it is.
Well, that
Decide yourself.
last one looked like it had an energy gain of 500, Mitchell.
At low input power, some of them actually even do better than that. The question is, do we gang them together, 1,000 of them, or do we figure out ways of bringing that energy gain for input powers of watts? And that's where we are right now, is to try and figure out which to do. 7.4 was interesting because a lot of people had said that at our course that we didn't show more than 100 milliwatts, which is, I pointed out, a different safety. So here we actually go up to 2 watts. And notice that the power gain falls down as we're hitting here at the watt level. We're dropping to I think this is half a watt or something. We're actually dropping down to a power gain of 3. And here at 1.5 watts input, we're actually dropping down to 1. Here we're having equal gain as we're getting out, so you can match. So you wouldn't want to drive this device more than a watt, because why? You may as well drive a resistor. But if you understand it and you know where to drive it, you have a chance of really coupling to the materials. Here's now this one's interesting. Nanor 7.7 has no PD in it. It's solely nickel. The one that we showed in Peter's lab during the IAP course was mixed palladium nickel with deuterium. This is solely nickel with deuterium. Here's our input to the OMA control. Here's our output. Here's the input to the nanor. Here's our output. These are far away detectors. And that's what we see here. Here's our input power normalized. This is the same 177. So here's our input power here, input power here. This will be our ratio. And yeah, that's log. So we're more than order of magnitude here. That's 7.7. So let's get to, and we see the energy gain as well for 7.7 with heat flow. If heat flow is normalized to input power, you can take that ratio too. See, it becomes flat. So we can get our energy gain by this to this. This is a different run. Notice I'm using very high voltages here. We're driving the system at a kilovolt, which is why when we get into avalanche, we run into so much trouble. We're measuring the current, and all of a sudden we're getting what went from a milliampere, a fraction of a milliampere to amperes, and say goodbye to the equipment. Okay. Here's our input power normalized. So here's our input output. Here's our input here. Here's our output here. Here again, this is the full board calorimetry of 7.7. Input and output's a nice match. Here's our input. Here's our input, and here's our output here. So the ratio is this to this is our energy gain. This is the power gain as a function of time. Okay, what we did is, for this one, here we see time, and now let's just do our energy gain. So here's our remote control, just under 1, and here's our device, which is has an energy gain of 3, drops down to 2, half 2. And what I wanted to try and do...
Why it's stepping down?
Because I want to go through the avalanche. Let me jump ahead and I'll show you. Remember what we saw was region 3, we lose the excess energy. Well, can we see it all the way through? And the answer is yes, we can. This was the first run that I ever did where we were able to show energy gain up to the avalanche, and you'll see what's on the other side. So for example, here we're looking at input power here from 0 to 1 watt. Here's our delta T, 0 to 3.5 degrees. And here's our control, input, output. Here's our control pre-avalanche, output. Here's the avalanche, here's post, and I'll show you the results. So when we look at the input power normalized to delta T, you know we take the ratio now. So here's our energy gain, ding, 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 ding. And after the avalanche, look at the match.
So
We've gone from absolutely showing cold fusion to where we've made it into a normal material. And if we plot it out here, we can see the same thing for input power. In fact, here it gets worse than the ohmic control. Here's our energy gain here. And when we go past the avalanche, we actually got less out there.
Mitchell, how fast has the avalanche occurred?
Fractions of a second,
Fractions of a microsecond, perhaps?
I don't know.
The reason I bring it up is that's going to create an enormous internal D field. You're blanking out your device.
Pardon?
You're blanking out your device.
Yeah. Or resetting it.
Those
Some-
were not treated previously, right?
I haven't looked. I'll get that for you though. Here, for example, here's the full board calorimetry. Here we see the ohmic control, nice match, see these are parallel. Getting good at this now. Here's our cold fusion. So we're getting our energy gain is this to this, this to this, this to about 3, 1.5, 2, 1.5. And here's our energy gain here as we separate. Here we're on the other side of the avalanche. And when we plot it out, here we see the instantaneous power gain. Ohmic control is 1. Here we see we're starting off around 5, coming down to 3, coming down to 2. We go through the avalanche, we're back in the ohmic control. Even though it's the nanor, we have lost the cold fusion effect on the other side of the avalanche. It's really
What
clear.
kicks off the avalanche?
High enough voltage to probably set up conduction pathways that weren't there before.
Now, does that change if you do the magnetic treatment?
Haven't done that yet. I haven't even added H to B. I mean, we don't have enough people, money, or funds. That's why you folks are here, is we need people. And if we had enough people and ability, we could know answers to these questions. And great questions.
Seems like you could control your avalanche by